when a force is applied over some distance. So if I have an object that I apply a force to, make this object, and I move it to another position, then I've done work on that object. Anytime I have a force that causes some object to move, then I've done work. Here, watch. I'm applying a force. Am I doing work on the object? No, I have the force, but the displacement of the object is 0. Or if I have an object that's moving that doesn't have a force applied to it, I can't have that, right? I can have an object moving at a constant velocity. There are no forces acting on it. That also has no work. So you have to have both the force and the displacement in order to give you work. So you need both force and a change in distance. When the force and the displacement are parallel, then we'll calculate our work in this way. We'll say work is just equal to the force times that displacement. The unit for work is the joule. And you need to know the basic SI units. Or actually, sometimes you'll see that people will use not a joule, but they'll use a unit of 1 Newton meter. And you might see me use that sometimes too. But this is the same. The Newton meter, Newton times meter, is equivalent to a joule. Joule is capitalized because it's a person's name. And the basic SI units, well, remember how we had a question like this on the last exam where you had to find the basic SI units. And I warned you that we're going to start seeing units that are more and more complicated. Make sure that you know how to determine those basic SI units. Since it's force times displacement, well, I know that force is mass times acceleration times displacement. Mass is kilograms. Acceleration is meters per second squared. And then distance, our displacement, is another meter. So those are our basic SI units. All right. Now, sometimes, often in fact, our force and our displacement will not be parallel. They won't be parallel or in the same direction. And so we'll have something like this where I have an object that has a force applied to it. I have an object with a force applied to it. That force has components in both the x and the y directions. So I have a component Fy in this direction, and then this is Fx. And of course that Fx is equal to F cosine theta. What is the displacement being caused by this force? Or is this force causing a displacement if I'm moving the object in this direction? None at all. So this force, or this component of F, is causing no displacement. As a result, this force does no work because it doesn't cause a displacement. So remember, just to step back a little bit, work is the product of our force and our displacement. In order to have work in this definition, the way we define what work is, we have to have both the force and the displacement. When they're parallel, the force and the displacement, it's just the product of those two. When they're not parallel, like this case, one of the components of the force, Fy in this case, does no work. All of the work that's done is done by Fx. And so we can create a more general equation for work that is F times d times cosine theta. And this is, just sort of as an aside, this is my x component of the force times the displacement, which is in the x direction in this case. All right, so this is sort of our catch-all for work, that is equal to the force times the distance times the cosine of the angle theta. As you're working work problems, this angle theta, there's never anything funny with it. You're always going to use this angle that's given. You'll see that when we work some problems. Like you're never going to do like 90 minus theta or anything of that sort. It'll always be the angle that's given. So if there's no displacement in the direction of the force, then there's no work done by the force. So for example, if I have this object and I'm applying a force to hold it up. Yeah, Olivia?
Sorry, what is
The first plate?
the?
oh, if F and D are not parallel, the component of the force that is parallel to D is the only component of the force that does work. So in this case, Fx is the parallel component, and it is the only force that does work. You can have a force and only part of it will do work, and the other part of it does nothing at all. Is that clear? Yeah. All right. So let's imagine that I have a bucket. This is my bucket of water, and I'm carrying it around. When I carry it around, I'm applying a force in this direction, as we talked about last chapter. Right, there's the weight pulling down. I have to exert a force going upwards. But what kind of work am I doing with that force? None at all, right? And if I move around at a constant velocity, meaning that no acceleration, what kind of work am I doing on this object? If I have constant or zero acceleration, rather, with a constant velocity. If I have zero acceleration, that means what kind of force? Zero force at all. And even though it's moving around with a certain displacement, there is no work being done. In order to have work, you have to have both force and a displacement in the same direction. So in this case, I have a force going up and a displacement in that direction, but still no work, because the force is perpendicular to the displacement. And that comes out in this equation, this sort of general equation that we have, FD cosine theta, because notice if F and D are perpendicular to one another, the angle theta then is what? That's 90 degrees. As we all know, the cosine of 90 is equal to 0. The cosine of 0 is equal to 1. And what is the cosine of 180 degrees? Negative 1. That'll become important in just a couple of minutes. Y'all with me okay so far? It's really not much more complicated than this. The problems will be more straightforward than we saw in the previous chapter. Okay, now dissipative forces such as friction can also do work, but they generally do negative work because the displacement and the force are in opposite directions. Remember, work is equal to F times D cosine of theta. Usually, almost always, friction opposes the direction of motion. So almost always, my frictional force and my displacement will be in opposite directions, because friction opposes the direction of motion. And so if F and D are in opposite directions, that means that theta equals 180 degrees. And as we said, while the cosine of 90 degrees equals 0, the cosine of 0 degrees equals 1. The cosine of 180 degrees is negative 1. You can think of this as tracing out the unit circle, where I have the x-axis is 1, the y-axis, the x component is 0, the negative x-axis is at 180 degrees, or negative 1. And so since that angle is negative, or is a cosine of 180 is negative 1, that means that F and D, or excuse me, the work due to friction is negative. Okay, y'all with me so far? Yep. I'm going to go on to the next page. Just a second. This negative, so far when we've had a negative value, usually the negative has denoted what? Direction, right? That's not the case here. The negative here does not denote direction. The answers are all up here. Okay, well, we'll figure that out. Usually we've been having negatives in direction, but work is a scalar quantity. work is a scalar quantity. This will come up again later, but let's go ahead and make a point of it here. Work is a scalar quantity that has no direction. You should be really happy for this, because this is why this chapter tends to be easier. Not easy, but easier than the previous chapter, because we're not dealing with vectors. And vectors are a real pain in the butt to deal with. Am I right? Vectors are kind of difficult to deal with. You got all those angles, and you got the trig you got to use, and it's just kind of a pain to use them. But because work is a scalar quantity, we don't have to worry about all that vector math, because it doesn't have a direction. So what does it mean for work to be negative? Well, what it means, we'll get to this in just a bit, but what it means is that objects or forces that do negative work take energy away. Right? Remember the frictional force? It does negative work. What does friction usually do to a moving object? Slows it down, takes away its motion, takes away its kinetic energy. So negative work typically, or negative work means that you're taking away energy. Let's look at these questions. Unfortunately, the answers are for every year I forget to take these off. But with these forces, which one does no work at all? What's the answer? It's A, right. There was a professor here, Jim Baker. Y'all probably don't know him. Y'all ever heard of him? He was, I don't know, he left 3, 4, 5 years ago. But one time he gave his students an exam, and they were taking the exam, and people started finishing pretty early, and he was kind of shocked because he was a pretty tough guy. Like his exams were tough. But he realized later that when he had made the exam, he had bolded all the correct answers, and he forgot to change the answers back to unbolded. So the students soon figured this out, that every correct answer was bold. Yeah, isn't that awesome? We should try that sometime. Or what if we bolded some that were correct, and then some that were incorrect? Yeah. Okay. All right. So let's just not play any tricks. We'll just bold all the right answers. Just bold all the right answers. Right. So which force does no work? This one does no work because the force and the displacement are in opposite directions. In each of these blocks, they're moving to the left in that direction, and so this one does no work because the force and the displacement are opposite directions. So work equals 0 here because the angle theta equals 90 degrees. Here, what about B? Positive, negative, or 0 work? It does positive work because the force and the displacement are in the same direction. Here the displacement is in this direction, so I have an angle of 180 degrees. Is that positive or negative work? Negative work. So that would be like the frictional force. And then over here I have this force. Only a component of this force is going to do work, Fx. It's going to do positive work, but the work done on object D will be less than the work done on object, B. Because this force is at an angle, you're going to get less work than you did here, because only a portion of that force, only a component is actually doing work. Okay? Work is force times displacement. When they're perpendicular, you do no work at all. When they're opposite one another, you do negative work. That means you're taking away energy. Friction usually is our example of something that does negative work. But you can have other forces that do negative work, right? Like I don't know, like football players, when you have the sled, right? Well, that's a frictional force too. Well, you get the idea. That anytime I have a force that's opposite the displacement, it is negative work. So when you lift an object, do you do positive or negative work? Well, let's think about it. So when you lift an object, that means that you exert a force pulling an object upwards. Are you doing positive or negative work? Well, what is the direction of the force that you're applying? You're applying a positive force. It's going upward, and you're causing it to move upward. What about the gravitational force? If I move an object moving in this direction, what is the gravitational force? Is it causing positive or negative force? It's causing negative force. So when I lift an object, I apply a force in this direction. This is the force due to me. The displacement is also in this direction. So work is equal to FD cosine theta, which is FD cosine of 0 degrees. So that is positive work. However, gravity, it acts in this direction, the force weight. So work is equal to FW, D cosine of 180, and that's equal to negative work. Okay? Go down. Okay. All right, let's try this, and then we'll do a few other clicker questions. I'm sorry, what, Maggie? Yeah, sure. Okay. You have some homework problems that are similar to this, but shopper in a supermarket pushes a cart with a force of 40 newtons. Find the work. All right, I'll stop at 150, 150. Okay, awesome. B is right. Again, not terribly complex. We're just looking to make sure that we know the right values that we're dealing with. Work equals FD cosine theta. F is 40 newtons. Our displacement is 25 meters, or that's the distance traveled. And then the angle between the two, between the force and the displacement vectors, is 60 degrees. Cosine of 60 degrees. And so my work is equal to 500 newtons. A is the right answer. Let's see, did I tell you about the two cats? One slid off the roof and one didn't? Yeah, the one that slid off, he had a smaller mute. I'm sorry, Matt, you want? What did I write? Yeah, it should be joules. Yeah, it should be joules. See, the mu is all right. Okay, so let's, before we get to the work energy theorem, let's do a few of these. asking about how that's going to affect the overall clicker grade. I scale it all, still won't affect you. If you're sort of where you need to be right now, right around that value that I said, maximum was 27, sort of with the sweet spot, if you want to be sort of around 24, 22, 23, that's okay. But if you're around that, then you're on track to get the full 50 points. That means that after the third exam, somewhere between the third and fourth exam, you'll say, oh, I'm all done now, and you'll have a couple weeks left in class. So don't sweat it too much. Just keep coming to class, keep getting the answers as correct. And if you're under 20, then you just want to really make sure that you're getting those answers right, because you get double credit. Is that clear what I mean? Yeah. Yeah, so that we missed a good portion of Chapter 4. Actually, there were a lot in Chapter 4 that we didn't do. It's not a big deal as far as your grade. It's not a deal at all. All right, I'm going to stop at 145. 145. I always feel like I'm giving up on y'all when I push the stop button. It's like, awesome. B is right. Remember, work is force times displacement. You have to have both a force and a displacement. If you don't have both of those, then you're not doing work. So it's not possible to do work on an object at rest. Let's see. Why didn't the son go to college? That is a good one. Because he already had 1,000,000 degrees. Or the alternate that William said was because he was already too bright. Oh, he wasn't too bright. Okay. Remember that. Okay. A box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? All right, I'll stop at 43, say, 43 or 45. Okay, good. Remember, friction almost always does negative work because friction opposes the direction of motion. If your motion's in one direction and your force is in the other direction, then that force is doing negative work. And remember, the work being negative doesn't have anything to do with direction because work doesn't have a direction. It's like mass or time or charge. It's a scalar quantity, so it doesn't mean anything in direction. What it means is that you're taking away energy. And friction is a good example of how forces can take away energy. Okay, we're going to skip this one. Do y'all have this one actually in your book? You do? Yes. Okay. The answer is yes. You can go ahead and put in yes. It's A. Friction can do positive work. We didn't actually do this last chapter, but there are some cases where you can have friction do positive work. Like, for example, if you're sitting in the back of the truck. Did y'all ever ride on the tailgate when you were kids? Yeah, we did. Like Mississippi, man, that's like the primary way of getting around town is riding on the tailgate. And hang your feet off the back of the truck. It's a good thing there that friction does a positive work because otherwise, if friction did negative work, it'd push you right off the back of the truck. As you're moving in one direction, the frictional force also moves you in that same direction. So you can have some cases where friction does positive work. Let me show you. Let me draw a picture to show you. So here's our truck, and here we are with our legs hanging off the back, our arms, like that. You know, if you had no friction between you and, your bottom, you would just slide right off the back of the truck because if there was no net force acting on you, then you would just stay right where you are. You would stay in your current state of motion. And so the frictional force, thankfully, actually pushes in that direction, even though the direction of motion is also in that direction. So in this case, friction can do positive work. So A is the right answer. I'm going to put in A. All right, 142, I'll stop. Okay, awesome. In a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Has the catcher done positive, negative, or zero work? I'm going to stop at 55, 58. We'll go to 58. Okay, we're a little bit divided on this. This ball is moving in this direction. The guy applies a force to it in that direction. Right? When it hits his glove, it moves a little bit after it hits his glove. The glove's cushioned, and it sort of moves the glove in just a little bit. And so our displacement is in this direction, but the force is in that direction. So which of these is right then? B is the right answer. B. It does do work because it Okay, now imagine that you have a ball tied to a string and it's being whirled around you in a circle like this. You're doing it like this. You have a ball on a string and you're whirling it over your head like this. What can you say about the work that's being done by the tension in the string? Think about what is the displacement, what is the direction of the tension force? We'll do about 10 more seconds. We'll stop at 103. Okay, very good. That's pretty good, actually. I didn't expect that good. So, as it moves around, we'll get to this in chapter 7 and 8, but as it moves around, the tension force is always towards my hand. It's always towards the center of the circle. But if you think about the displacement, as this thing moves around in a circle above my head, the displacement is always tangent to the circle. I know it seems like it's zero, but if I imagine this, I have it, the tension force is always in this direction, and the displacement is always in that direction. We'll get to this in chapter 7 again, but for now, all we need to know is that these are opposite, are at 90 degrees to one another, that then the work done by tension is zero. So A is the right answer. You lift a book with your hand in such a way that it moves up at constant speed. While it is moving, what is the total work done on the book? This is the total work that's being done on the book. Okay, about 2/3 of you have the right answer, and about 1/3 don't. But when we're looking at the total work is the sum of all the individual works. So think about what that means to the work that's being done on here. What is the sum of all the individual works? Or you can further think about this as what is the sum? What is the work being done by the net force, which would be the same answer. I'm going to stop here at 125. Okay, good. D is right. We're going to get to this later, but when we want to know the total work that's being done, I can calculate the work done by one force. This would be positive work, right? The work done by another force, this would be negative work. And then the total work would be the sum of them, the positive work plus the negative work. Or I could also think about the net force. The net force is the total force that's being acted upon this book, that is acting upon this book. That net force is equal to 0. And since the net force is 0, there's 0 work. Always do a couple more. Actually, no, let's stop there. Not stop. So now let's look at kinetic energy. Kinetic energy is the energy of a moving object. Kinetic energy, we're not gonna derive it. I'm just gonna give it to you. You have to you get it through calculus, but it's 1/2 m times v squared. That is our kinetic energy. It is a scalar quantity, just like work. The units are the same. I think I give these to you later, but let me go ahead and write them here. The units are also joules, which is the same as what we had for work. In fact, we'll find that work and energy are closely related. We'll look at the work-energy theorem, where if I do work on an object, it changes the energy. Now, an interesting relationship. People used to think that kinetic energy was proportional to the speed v. They used to think that back in the, 1700s and prior to that, that the energy of an object was proportional to v. That if you went faster, say twice as fast, you had twice as much energy. And this lady, Emily de Châtelet, I think it was the late 1700s, she came along, she did an experiment where she dropped a steel ball into clay. And she found that it made an indentation in the clay. And its indentation was, some depth, we'll call it h. And then she took the ball, say the ball strikes with speed v, she took the ball and she dropped it from a higher height so that it struck at the clay with twice the speed. And what do you think that she found? Well, that if we believe this is true, by how much should this be different? It's going to double, because the depth of your pit, if you will, or the indentation, is proportional to the amount of energy. So if it is true that KE was proportional to V, then what I should have here is one that is twice as deep. But what did she find? Not same. It was what? It was proportional, yeah. But instead of saying KE is proportional to V, I know that KE, as I just told you, is proportional to V squared. What happens if you double the speed to the amount of energy? It's going to be 4 times as steep. Because KE is not proportional to V, the kinetic energy is proportional to V squared. And so the height, or the depth of this indentation, would not be 2h, which is what everybody thought, but it was 4h. The reason for this, people thought that squared numbers, they didn't want to believe that kinetic energy was proportional to the speed, because they thought that squared numbers were evil in some way, like literally evil. They thought that they were from Satan. I mean, you might think that sometimes too, but they thought that literally squared numbers were an abomination. And it's kind of silly. I mean, it's silly for us now to think that, right? Because it's just multiply two numbers together. And in fact, it was silly for them too because they used squared numbers a lot back in the 1700s. What did they do that would require using squared numbers a lot? They were mostly, you know, people mostly farmed, right? They grew their food, they would sell their food sometimes, they'd have cattle, but in farmers, they have to use square numbers a lot because you have to calculate areas of fields and the yield of your seeds, and so it was kind of silly, even though that was really what they believed, but it was kind of silly just because they did use square numbers a lot. Let's stop there. I want to hand out your exams. Need a few minutes. But we'll probably wrap up this chapter on Monday. It's a short chapter, not a lot in it. So Monday, maybe a little bit into Wednesday, but not long after that.